Dear friends, I am Dr. Pushpal Ghosh, Assistant Professor, Department of Chemistry, Dr. Hari Singh Gaur Vishwavidyalaya, Sagar. Today, I will discuss with you about the wave-particle duality. In last class, we have discussed about relation between the spectroscopy and chemist. Today, we will discuss how the concept of wave-particle duality arises in the quantum mechanics, photoelectric effect, de Broglie hypothesis, Heisenberg uncertainty principle, and then I will summarize my lecture. So, wave-particle duality is a very important concept which states that every particle or quantum entity can be described in terms of not only waves but also as particles. Ibn al-Haytham, an Arabic scientist in the 11th century, demonstrated in his book of Optics or Kitabul Manazir that the light or rays were composed of particles of light. Sir Isaac Newton developed corpuscular theory of light and emphasized that the perfectly straight lines of reflections indicates particle nature of light. Around the same time, Huygens, Robert Hooke and later Fresnel developed the wave viewpoint mathematically, and their views were supported by Thomas Young's discovery of wave interference of light by his famous double-slit experiment in 1801. In 1860s, James Clerk Maxwell applied his equations to describe shell propagating waves of oscillating electric and magnetic field, and very soon it was perceived that visible light, ultraviolet light and infrared light are all electromagnetic waves with different frequency. Again, in 1887, Maxwell's prediction of the existence of electromagnetic waves was confirmed by Hertz, which was explained in my last lecture. So, it was not clear to the scientific community until first end of 20th century about actual nature of light. Earlier, blackbody radiation and quantization of energy is nicely explained by Max Planck. While Max Planck had solved the ultraviolet catastrophe by using a quantized electromagnetic field, but there were some issues still. However, Einstein used Planck's blackbody model to solve another important problem of that time called photoelectric effect, wherein electrons are emitted from atoms when they absorb energy from light and would lead to an electric current in a circuit. Albert Einstein in 1905 gave an explanation of the photoelectric effect which was not explained by the wave theory of light. Einstein postulated the existence of photons and quanta of light with particulate qualities. First, it was assumed that light was knocking the electrons, but in case of potassium, it was observed that a dim blue light was able to create current. However, brightest red light was not able to create that current. This observation was certainly not according to the classical theory, which says that strength of amplitude of a light is in proportion to its brightness, that is, a bright light should easily create a large current. But this was not observed in case of potassium when bright red light was used. So, this figure 1a is showing the schematic diagram related to photoelectric effect. Now, let us discuss the photoelectric effect. Light of frequency nu hits the emitter E, and with the help of a potential difference B between the E and the collector C, photoelectrons and photoelectric current can be produced and can be measured. So, this can be seen from the figure 1. Now, figure 2 depicts a plot of I, that is current, versus V, that is potential difference. It is seen that with increase of V, current increases and finally reaches a constant saturated value, which can be seen from figure 1a. Now, if V is made 0, I does not come down to 0. This happens because electrons are emitted with certain velocity and may reach the collector on their own urge. But I can be made 0 by reducing the potential to a negative value V0, which is called as stopping potential. Now, this V0 times the charge of an electron gives the kinetic energy of the most energetic photoelectrons. So, we can write the Kmax is equal to E into V0. Now, keeping nu unchanged, if the intensity of the light is doubled, though the saturation current gets doubled, but V0 remains the same. So, it can be said that V0 and Kmax are both independent of light. This is very important. Now this figure 2 is showing variation of current versus stopping potential, and figure 3 shows the variation of the stopping potential versus nu. So a straight line is obtained and there is a threshold cutoff frequency at which V0 is equal to 0 is observed. That means no light below this frequency, however high intensity it has, is able to produce photoelectrons. So there are three special features related to photoelectric effect which cannot be explained in terms of classical physics but solved by the Einstein hypothesis, and those I will explain now. One is the intensity problem. From the classical point of view, as the intensity of the light is increased, the amplitude of the oscillating electric field also increases. Since the force exerted on the electron is small e into capital E, this suggests that the kinetic energy Ke of the photoelectrons must also increase with the intensity of light. But it is found from the experiment that V0 and Kmax is independent of the intensity of the light. Now another problem is a frequency problem. Classical physics expects that photoelectron can be ejected for any frequency of light, provided it is intense enough to expel the electrons from the skin of the metal. But from the experiment, it is mentioned that for each surface there is a cutoff frequency below which the photoelectric effect does not occur, no matter how intense the illumination. Another important problem is time lag problem, because a definite time lag is required for an electron to soak up sufficient energy from the wavefront, but the above experiment suggests that there is no time lag between the incidence of light and ejection of the photoelectrons. Both the processes is instantaneous. So you can see that figure 3 shows the variation of stopping potential versus nu. Now Albert Einstein solved these issues with his new approach. What he suggested? He suggested, or he pointed out, that the radiation is itself quantized. The light beam consists of packets of energy known as photons. The energy of a single photon is h nu, and where nu is its frequency. So by increasing the intensity of a light beam means an increase in the number of photons per unit volume. Now in order for an electron to be ejected, it must receive energy equal to its binding energy, which is called the work function for the metal involved. If the frequency is so low that h nu is less than the work function, then electron can't be ejected. Hence the threshold frequency is very much important. The work function phi is equal to h nu 0, where h is a Planck's constant. Its value is 6.626 into 10 to the minus 34 joule second. Emission occurs only when h nu greater than phi, and any excess of h nu over phi appears as the kinetic energy of the electron. So we can write Kmax is equal to h nu minus phi, and we can write that capital V0 is equal to h nu by small e minus phi by small e. So we can simplify it further, h nu by small e minus h nu 0 by small e. So this was actually observed in the figure 3. Finally, since the photons are concentrated energy bundles and the transfer of energy from the radiation has been through a photon transferred to its entirely to a single electron, no time lag observed between the incidence of light and the ejection of the electrons. So this is the beauty of the Einstein hypothesis, and he solved which classical mechanics did not solve. And for that reason, in 1921, Albert Einstein was awarded Nobel Prize in Physics for the discovery of the law of the photoelectric effect. And here we must remember that here we are showing the particle nature of the light wave. Now we will explain understanding the de Broglie hypothesis and its significance. So you know that researchers have always been fascinated by the symmetry of the world. Light, which was considered to be a wave, just I have explained, is now have a particle-like behavior, which you have seen from photoelectric effect. So it is not unwise to expect particles having wave-like properties. In 1924, Louis de Broglie proposed that as light has both wave-like and particle-like properties, electron also have wave-like properties. So it can be hypothesized that with any moving body, there is associated wave, and that the momentum of the particle and the wavelength of the associated wave, which are related by the famous equation lambda is equal to h by p. Here I must mention that this work of de Broglie was of only 3 pages, and he got the Nobel Prize for this, because he explained here that any matter, whatever its size, whatever its weight, it can have or has an associated wave. So by this equation, he got that impression that lambda, which is the wavelength of any matter, can be expressed as h by rho or h by p. And this equation was derived from the Einstein famous equation that says energy is equal to E is equal to root over m square c to the power 4 plus p square c square, where m is the rest mass and p is the momentum. For a photon, E is equal to h nu and rest mass is 0. So we can write h nu is equal to p into c. So we can write c by nu is equal to lambda is equal to h by p. P is the momentum, and by this we are getting this great equation, which bridges between the classical mechanics and quantum mechanics. I must mention here again that this de Broglie's famous equation make bridges between the classical mechanics and the quantum mechanics. So now we are able to understand the dual character of the matter, that is, matter wave were first experimentally demonstrated by George Paget Thomson's cathode ray diffraction experiment and the Davison-Germer experiments for electrons. In 1927, at University of Aberdeen, G.P. Thomson observed the diffraction of electrons by a thin film of celluloid. Eventually, his father J.J. Thomson was also awarded the Nobel Prize for showing that electrons are particulate, and he himself along with Davison shared the Nobel Prize for physics in 1937 for their experimental work. Here I must mention that similarly Marie Curie family got several Nobel Prizes. Also the famous Bragg family also got Nobel Prize, where son and father both got Nobel Prize. Now de Broglie was also awarded Nobel Prize for physics in 1929, and his formula, which I just explained, was confirmed 3 years later in a brilliant experiment designed by Clinton Joseph Davison and Lester Hurlbut Germer at Bell Laboratory. What they have done? They fired slow moving electrons through a double slit at a crystalline nickel target and then measured the angular dependence of the diffracted electron intensity. The same diffraction pattern as those predicted by Bragg for X-rays was observed here also. So both these experiments of Davison-Germer and Thomson proves de Broglie's hypothesis of dual character of matter, both as a particle and a matter. Now I will explain electron as a matter wave and Bohr's momentum quantization. So now let us consider an electron in an orbit. Then for most momenta and radii, the waves associated with the particle will interfere destructively as they overlap around each orbit. Only for some radii and momenta will the ends of the waves on each orbital circuit join, so that non-destructive interference occurs. For this to occur, the circumference of the orbit must fit an integral number of the wavelength of the wave associated with the electrons. So the condition will be 2 pi r is equal to n lambda, where n is equal to 1, 2, 3, any integer. So using the de Broglie equation, we can write lambda is equal to h by p, and lambda is equal to h by mv, because p is just momentum mv. And we can replace this 2 pi r by h is equal to h by mv, and we can get mv is equal to nh by 2 pi. So this is called the momentum quantization of Bohr. This is also very important. Now I will come to another important hypothesis, which is called Heisenberg uncertainty principle. A significant problem in classical mechanics is the finding of the values of various dynamical variables of a system like momenta and coordinates, energy and time at one instant. Generally, the motion of a system of f degrees of freedom requires the knowledge of f momentum and f position coordinates. It is also normally considered in classical mechanics that this entire two-way variable can be determined with any desired degree of accuracy. Actually, this is not true. Classically, you cannot get it. So, in this context, Werner Heisenberg postulated his uncertainty principle. The principle says that for each system, there are certain sets, that means member may maximum be 2, of conjugate variables like x position coordinate and x component of the linear momentum, energy and the time coordinate, angular momentum along two axes, let us say x and y, which cannot be determined simultaneously. There will always be certain uncertainties in their values, so that the product of the two uncertainties will be either greater or at least equal to h cross by 2, and h is called h by 2 pi. So, we can write here the delta x into delta px greater than is equal to h cross by 2, delta y into delta py greater than is equal to delta h cross by 2, delta E into delta T greater than is equal to h cross by 2, and delta Mx into delta My greater than is equal to h cross by 2. Delta here indicates the standard deviation and a measure of spread or uncertainty. So, Heisenberg eventually explained this phenomenon as a consequence of the process of measuring, that is, measuring position accurately would disturb momentum and vice versa. So, this was diligently confirmed by the so-called gamma ray experiment, which crucially depends on the de Broglie hypothesis. So, we can conclude the idea of uncertainty principle directly comes out from the wave particle duality. Now it is time to summarize my lecture. So, in this module, we have learned several important observations where every particle or quantum entity can be described in terms of not only waves but also as particles. I have explained blackbody radiation, quantization of energy, and separately ultraviolet catastrophe in my last lecture, and here also I have explained how it is nicely correlated by Max Planck's theory. It is explained in the lecture how Einstein used Planck's blackbody model to solve another important problem of the time called photoelectric effect and their different aspects, where electrons are emitted from atoms when they absorb energy from light and would lead to an electric current in a circuit. Einstein also shown that not only the intensity of light, however, the frequency of the light is also important for releasing or for ejecting the photoelectrons from the skin of a metal. Einstein's theory also very accurately solved the intensity, frequency and time lag problem, which cannot be solved by the classical physics or based on the classical outlook. Later, just a few years later, Louis de Broglie hypothesis proves that just as light has both wave-like and particle-like properties, electrons and also other matter, any matter, can also have wave-like properties. This was further proved experimentally by Davison and Germer and G.P. Thompson's experiments. Now, Bohr's momentum of quantization is nicely explained using de Broglie's hypothesis. Now, finally, Heisenberg's uncertainty principle is discussed. The principle says that for each system, there are certain sets where member may be 2 of conjugate variables which cannot be determined simultaneously. There will always be a certain uncertainties or inaccuracy in their values, so that the product of the two uncertainties will be either greater or at least equal to h cross by 2.